The next part of this section is what we call the first derivative test. Now, the first derivative test just basically adds a step to the process we were doing before, but it allows us to determine all of the relative minima or relative maxima for a function. So basically, if you let c be a critical number of a function that's continuous on an open interval, if f is indifferentiable on that interval except possibly at the point c, then f of c is a relative minimum if f prime of x changes from negative to positive at c. It's a relative maximum if it changes from positive to negative, and if it's positive on both sides or negative on both sides, then it's neither. So you can see these cases here. If we're changing from decreasing to increasing, it forms a dip in the graph, so that would be our valley or our relative minimum. If it changes from increasing to decreasing, it forms a hill in the graph, so that would be our relative maximum. And these are some of the cases like that x cubed graph we looked at in the previous video where you may have a critical number, but it doesn't necessarily mean it's a minimum or a maximum. So those are the cases that we're going to look at. So let's do an example. We're going to take 1/2 x minus sine x, and we're going to check on the interval from 0 to 2 pi. So the first thing that I want to do is find my critical numbers. So I'm going to find the derivative f prime of x, which is going to be 1/2 minus cosine of x, and I'm going to set that equal to 0. So cosine of x is equal to 1/2. And we know that from our 30, 60, 90 triangle and from our unit circle, that the angle that has a cosine of 1/2 would be the 60-degree angle, so that's pi over 3. And since we're between 0 and 2 pi, we need the pi over 3 this way and this way would both give us a positive 1/2 for our x. So that's going to be 5 pi over 3. So you take the 2 pi and subtract pi over 3. So those are my two critical values. So if I set up intervals, I'm just going from 0 to 2 pi, so I would have from 0 to pi over 3. I would have from pi over 3 to 5 pi over 3. And I would have from 5 pi over 3 to 2 pi. So I still need to pick up test points. And I want to pick something that's in the interval that's easy. So a number that's between 0 and pi over 3 might be pi over 6, because I can find the cosine of that pretty easily. From pi over 3 to 5 pi over 3, why don't we just pick the pi, because that's super easy to find the cosine of. And for the other one, we could do the negative pi over 6, which is coterminal with 11 pi over 6. So those are going to be my test points. I'm going to evaluate f prime of x at each of those. So here I'm going to have 1/2 minus cosine of pi over 6, which is 1/2 minus the square root of 3 over 2. And the only thing I care about is that that's negative. Here we're going to have 1/2 minus cosine of pi, which is 1/2 minus negative 1, or 3/2, which is positive. And here we'd have 1/2 minus cosine of 11 pi over 6, which is going to be, again, 1/2 minus root 3 over 2, which is less than 0. So we want to talk about where it's increasing and decreasing. So here we'd be decreasing, here would be increasing, and here we'd be decreasing again. So you can see when you go from increasing to decreasing that this forms a minimum. And when we go from increasing to decreasing that this forms a maximum. Now I do need to know where this happens. So I am going to pick, I'm going to find the y value. So I'm going to find f of pi over 3, which would be 1/2 times pi over 3 minus sine of pi over 3, because that was the original function. We just want to find the y value. You always go back to the original function. So that's pi over 6 minus root 3 over 2. And if I wanted to find f of 5 pi over 3, that would be 1/2 times 5 pi over 3 minus sine of 5 pi over 3. So that's 5 pi over 6 minus negative root 3 over 2, or 5 pi over 6 plus root 3 over 2. So that means we have a relative minimum at the ordered pair, pi over 3, and then pi over 6 minus root 3 over 2 is the y value. And we have a relative maximum at the ordered pair, 5 pi over 6 plus root 3 over 2. I'm sorry, 5 pi over 3, 5 pi over 6 plus root 3 over 2. So those would be my relative extrema for this function. So for this one, I'm going to automatically note for the domain x cannot equal 5. So that is going to have to be a boundary point. When we want to find the critical numbers, we need to find f prime of x. So here we have to use the quotient rule. So f would be x, and g would be x minus 5. So f prime is 1, g prime is 1. So this is going to be low di minus high d low over low low. So that would be 1 times, x minus 5 times 1 minus 1, minus x, getting this backwards today, times 1, all divided by x minus 5 squared, which is x minus 5 minus x over x minus 5 squared, which is negative 5 over x minus 5 squared. So this doesn't exist at the same place where f of x doesn't exist. So f prime does not exist at x equals 5. This is not a critical number because f doesn't exist, but it is a boundary. So we need to keep that in mind. And because the numerator is negative 5, f prime is never going to be equal to 0. So just keep that in mind. So what that means is we don't actually have any critical numbers. We do want to check what's going on here. If you don't have any critical numbers, you're probably not going to have any extrema, but let's just see what happens if you follow through with the test. Our test numbers would be, we could do 0 and 6 or 0 and 10 or whatever you want to do. So when you're plugging that into f prime of x, you'd have negative 5 over 0 minus 5 squared, which is negative 5 over 25. Again, all we care about is that it's negative. And here you'd have negative 5 over 6 minus 5 squared, or negative 5, which is also negative. So you can see that on this side it is decreasing, and on this side it is decreasing. So this is not a relative min or max. So in this case, there are no relative extrema. Now, just as a side note, if you had been asked to find the intervals where this was increasing or decreasing for this function, you would say it was decreasing from negative infinity to 5 and 5 to infinity. You don't want to put those together because it's not decreasing on the whole interval because x cannot be equal to 5. So there is a break in continuity there. Now, the last thing I want to point out is the difference between finding the relative extrema of a function and finding the absolute extrema on a closed interval like we did in 3.1. So if it says to find all relative extrema, you want to go through the new process here. So f prime of x would be 2 minus 1 over x squared, which would be 2x squared minus 1 over x squared. The domain here, again, is that x cannot be 0. So that's not going to be a critical number, but it's not going to be in the domain. So, so it does not exist when x equals 0, and f prime of x equals 0 when the numerator, 2x squared minus 1, equals 0. So that gives me x equals plus or minus the square root of 1/2, or plus or minus root 2 over 2. So when I set up my intervals, I'm going to go from negative infinity to negative root 2 over 2. I'm going to have negative root 2 over 2 to 0. I'm going to have 0 to root 2 over 2. and I'm going to have root 2 over 2 to infinity. And if you need to remind yourself somehow that it just actually doesn't exist at 0, you've got an asymptote there. There's nothing wrong with just drawing a dashed line or making some kind of notation that helps you remember that. So let's pick our test points. Negative root 2 over 2 is about negative 0.7, so we could pick negative 1. Here I might want to pick something like negative 1/2 because I can't pick an integer, negative 0.7 to 0. Here I'll pick positive 1/2, and here I'll pick positive 1. So when I go to find f prime of x, I'm plugging into this right here. So I'm going to have, I'm just plugging this in on my calculator, so if you hear me clicking away over here, that's what's going on. So here that gives me a 1, which is positive. I plug the negative 1/2 in, I get a negative 2, which is negative. If I plug the 1/2 in, I get a negative 2, which is negative. And if I plug the 1 in, I get a 1, which is positive. So from there, this is going to be increasing, decreasing, decreasing, increasing. And you can see that this would be a max, this would be neither, and this would be a min. So we have a relative max at the point negative root 2 over 2, and then I'm just going to plug root 2 over 2 into this function. So let me get some space and do that. So you can see over here I've just plugged them into the function to find the y values, so that's going to give me negative 2 square root of 2, and I'm going to have a relative min at negative root 2 over 2, I'm sorry, positive root 2 over 2, and then positive 2 root 2. So that would be my answer. So that is finding the relative extrema of the function. Now in 3.1, you were asked to find the absolute extrema of a function on a closed interval. So again, this is finding the critical numbers first. So again, you find the derivative. I'm not going to go through the work of that, but you get 2x squared minus 1 over x squared. And because the only place where this exists everywhere in the closed interval, because the only place that it doesn't exist is 0. So we're okay there. And f prime of x is equal to 0 when 2x squared minus 1 equals 0. And we already found that this was plus or minus root 2 over 2, but we don't need this because we're in the interval from 1/2 to 2, and negative root 2 over 2 is not. So we're going to check the y values at the critical number and the endpoints, and then we're going to just compare the raw y values here. So f of root 2 over 2, which we did earlier, we found that that was 2 square root of 2. F of 1/2 would be 2 times 1/2 plus 1 over 1/2, which is 1 plus 2, which is 3. And f of 2 would be 2 times 2 plus 1 over 2, which is 9/2. Now, if we're just comparing these values, this is about 2.83. This is 4.5. So obviously this is going to be the minimum, and this is going to be the maximum. So we have an absolute minimum at the point root 2 over 2 to root 2, and we have an absolute maximum at the point 2 9/2. So you can see the difference between the two. If you want to find relative extrema, you need the first derivative test, but if you want to find absolute extrema on a closed interval, you just plug things straight into f of x and compare the y values. So make sure when you're working the homework and going through the problems that you are clear about which type of problem you're trying to solve.